Now that we've introduced spherical coordinates, our goal here is going to be to evaluate triple integrals in terms of spherical coordinates. What that means is we're going to get a new description of the region of integration. There will be some sort of area distortion factor. And as always, the form of our function may need to change. We are going to talk about the simplest domain in spherical coordinates, and this will be what we call a spherical box. Now, I'm putting it in quotations because it isn't going to be the usual straight-walled box from Cartesian coordinates. The box means that we'll take our radial value to be from A to B, our theta value to be from alpha to beta, and our phi value to be from some angle gamma to delta. So how does such a box look like? We're going to have something that looks like this. Now, it takes a little bit of time to get used to drawing such things, but I'll try to explain it to you here. We are tracing this down to some difference in theta values. Theta is alpha, theta is beta. At the same time, we've got two different angular values here for the polar angle. We'll have gamma and then delta here. Our radial values are now going from some A to B. Now, to begin this conversion process, what we need to do, as always, is partition all of our variables, and we'll use a regular partition with n subintervals. We don't have to take equally spaced subintervals. We don't have to take the same number of subintervals for all of our variables, but to simplify the process, we will do so. Row variable will be partitioned from row naught, row 1, all the way up to row n, where this first one is A, the last B. We will have some general radial location indexed by I and A plus I delta rho, where delta rho is simply B minus A over n. Our theta variable will be partitioned from theta naught, which is alpha, theta 1, all the way down to theta n, which is beta. Our theta variable will be indexed on J, alpha plus J delta theta, and delta theta is beta minus alpha over n. And finally, our phi variable will be partitioned phi naught, phi 1, where phi naught is gamma, all the way down to phi n, where this is delta. And our phi variable will be indexed on k, gamma plus k delta phi, where delta phi is just delta minus gamma over n. So what this ends up doing is it subdivides our spherical box into small spherical boxes. We take that same spherical box, it gets cut up into many little subdivisions, and we've cut it in all the directions. And what we end up doing is taking out one small box Bijk here. And what we're going to want to do now is determine the volume of this small box. Now, this box Bijk we can think of as the Cartesian product from row of I minus 1 up to row I with theta j minus 1, theta j, and then phi of k minus 1, phi of k. This is the mathematical description of all the different points in this box. Now, our goal here is to determine what the volume of this box is. Now, unfortunately, it's going to be very hard to choose the right shape and find the lengths. We're going to take a little bit of a roundabout route. What we're going to do is start with our friend the ice cream cone from the previous video. Now, an ice cream cone is essentially a spherical cap on top of a cone like this. And up here, we've got a sphere that's given by some rho equals rho naught is a constant. Down here is some cone that's described by phi is at some angle phi naught, which is a constant. If you use cylindrical coordinates and triple integration. Now, this is an exercise in and of itself. It isn't immediate, but you can show that the volume of this ice cream cone ends up being 2 pi, which comes from the theta variable 1/3 rho naught cubed, 1 minus the cosine of phi naught. So the next step here is for us to take a slice of this ice cream cone. Draw it on some coordinate axes, just like this. What we're going to do is talk about two different angular values, and we're going to take a slice of this cone with respect to theta. One slice will end up looking something like this. If we were to take this out, this is the type of shape we would see. rather than having a 2 pi in the front, which came from a full rotation, the volume of this particular slice, this is going to be theta 2 minus theta 1 times 1/3 of rho naught cubed, 1 minus the cosine of phi naught. So now if we let theta 1 be theta of j minus I and theta 2 be theta of j, our two generic values, then this theta 2 minus theta 1 is simply our delta theta. So the volume of this slice is just 1/3 rho cubed 1 minus cosine of phi naught delta theta. Because this delta theta pops in, this is the motivation to go on to the next argument. What we're going to try to do is consider other small changes in rho and in phi. So the next place here to go is to talk about a small change in this radial value. So we're going to take the difference in slices when we go from rho of I minus 1 up to some rho of I, two generic radial locations. Now, it's easiest if we talk about this in our side view. Here is rho I minus 1. Here is rho I. So if we had a slice that lived at rho I, we've got our fixed angle phi naught like this. If we now subtract from it a slice that lives at radius rho I minus 1, so a slice at the same angle phi naught, that slice has that particular volume. So if we subtract the two of these, what we will end up with is a region that looks something like this. Rho I minus 1, rho I, something at this angle here. We'll get this region in there. So this volume right in here is the difference in the two results that we had from above. We'll have a 1/3 rho I cubed 1 minus cosine of phi naught delta theta, subtract 1/3 rho I minus 1 cubed 1 minus cosine of phi naught delta theta. So if we simplify this, we'll get a 1/3 rho I cubed minus rho I minus 1 cubed 1 minus cos phi naught times delta theta. Now the final thing we're going to do is consider a small change in phi, from phi of k minus 1 up to phi of k. Remember that this means that our delta theta change is basically going in and out of the page here. So what we've got is our rho I minus 1, our rho I. This makes two radial rings. If we live at some angle phi k over here, we've got one of these wedges from before. Now what we're going to do is subtract from it another little wedge. We're going to label our same radial values, but this time the angle will live at a different value. So this will be at phi k minus 1 rather than phi k. So it will end up being this little wedge. What this produces is a small spherical wedge. And that small spherical wedge now considers changes in all three of our coordinate directions. The volume of this thing is a difference in the two expressions that we had from before. So what we have is a 1/3 rho I cubed, rho I minus 1 cubed, 1 minus cosine of phi k delta theta, subtract 1/3 rho I cubed, rho I minus 1 cubed, 1 minus cosine of phi k minus 1 delta theta. We'll have a 1/3 rho I cubed minus rho I minus 1 cubed, 1 subtract cosine phi k, subtract 1 minus cosine of phi k minus 1 delta theta. These ones will subtract out. And now what we'll get is this following expression. Cosine of phi k minus 1, subtract cosine of phi k, delta theta. This turns out to be the volume of this small spherical box, Bij. But unfortunately, it isn't in the right form. Eventually, what we're going to want is to have a Riemann sum. We also need a delta rho and a delta phi as well. There is a way for us to generate it, though, and this is very useful application of the mean value theorem. Let's say we have this function g of rho, and we're going to call it rho cubed, and it's going to be defined on our box rho I minus 1 to rho I. G is definitely continuous on that closed interval. G prime of rho is 3 rho squared, which means this exists on the open interval, which implies that G function is differentiable on our open interval. That means we've got the mean value theorem condition satisfied, so the conclusion of the mean value theorem holds. There exists some sort of rho I star somewhere between those 2 points on the open interval, so that the derivative of my function at that rho I star is going to be g of rho I subtract g of rho I minus 1 all over rho I subtract rho I minus 1. If we substitute everything in, we'll get a 3i star squared, because that's the derivative, rho I cubed minus rho I minus 1 cubed delta rho. The expression inside of our delta volume has this term, and we get extra lucky here in that 1/3 rho I cubed minus rho I minus 1 cubed, which is the thing in our delta volume. This now ends up being a rho I star squared delta rho. We got the delta rho that we're looking for. If we let h of phi equal to cosine of phi on this subinterval phi k minus 1 into phi k, our function h is continuous on this interval simply because it's a trig function. H prime of phi is negative sine of phi. This function h is differentiable on this open interval. And by the mean value theorem, because now the conditions hold, there has to exist some phi k star that lives between those two numbers, such that h prime of this phi k star is h of phi k subtract h of phi k minus 1 all over delta phi k. If we substitute everything in, we'll get a negative sine of phi k star cosine phi k subtract cosine phi k minus 1 over delta phi. So at the end of the day, the thing that we have in our delta volume, which had these in the reverse order, this is now going to end up giving us a sine of phi k star delta phi. That's exactly what we're looking for. So putting this all together, the volume of this box Bij, we had a 1/3 difference in these rho values. This is going to end up giving us a rho I star squared delta rho. The difference in those cosines is going to now give us a sine phi k star delta phi, and we had a delta theta from before. Reorganizing it, we'll get a rho I star squared sine of phi k star delta rho delta theta delta phi. This is exactly the form that we want. As always, we're going to define the hypervolume of the function above this box. We're going to approximate it as the value of the function at this rho I star, some theta j star, and this phi k star times the volume of this box. The total hypervolume is approximated. Now, it's an approximation because we are holding this constant over the entire box. The total hypervolume is going to be the sum of all of these boxes. So we'll have a sum I equals 1 to n, j equals 1 to n, k equals 1 to n function at that sample point, which lives somewhere in the box, rho I star squared, sine of phi k star, and then we'll have a delta rho, delta theta, delta phi. As before, this triple sum ends up being a Riemann sum for this function in the blue box. We're going to make an assumption that if f is continuous on our full box B here, this Riemann sum will exist. And if this Riemann sum exists, that means that this function f is integrable, and at the same time looking ahead, it will mean that this function f times rho times a sine phi is also integrable, because those two are continuous functions. And that means we can define the hypervolume as essentially this triple integral in spherical coordinates. Over that spherical box will now end up being the limit as n goes to infinity of this triple sum, this stuff in the blue box, which I'm not going to write down, times a delta rho, delta theta, delta phi. As before, this is going to boil down to an integral a to b, alpha to beta, gamma to delta, f of rho, theta, and phi, rho squared, sine phi, d rho, d theta, d phi. We will have a new description, and this, most importantly, is our area distortion factor. Now, as always, by Fubini's theorem, we can interchange the order because all of these terms are continuous. If we're going to talk about a general region in R3, we'll call this some region E. We've got our blob here is E. What we need to do is enclose this in some sort of spherical box, and we'll call this box B, and then we define our extension function. This extension function will be equal to the original function. If we are in the general domain, it'll be equal to 0. If we are in the box but not in that general domain, this thing is piecewise continuous. That means that the integral will still exist when we consider the integral of this extension function over the full box. And as before, this will simply boil down to integrating our original function over the limits of that box. The hard part is, how do we describe this in spherical coordinates? And that's the topic we will talk about in the next video.